Hi friends, this is the ninth lecture in the lecture series for the preparation of getting mechanical engineering. Today we will be dealing with lumped capacity analysis. Lumped capacity analysis, and this is the continuation of the last lecture. So please go through the last lecture for getting a better clarification or better understanding. So consider a particular body which is having a uniform temperature T and some fluid is flowing outside this body at some temperature T infinity, and the convective heat transfer coefficient will be H. So suppose this temperature of the body is greater than temperature of the fluid that is outside, so heat transfer will be occurring from the body to the fluid that is outside. So we can write energy balance for this body as energy balance. We can write Q dot in minus Q dot out will be equal to du by dt, where u is the internal energy. So we can see that there is no heat is entering into the body, so this Q dot in is equal to 0. So we can write minus Q out will be equal to du by dt, and this Q out is occurring by conversion. So we can write this as minus HAS T minus T infinity will be equal to rho into C into V into dt by dt. Okay, and this AS is the surface area of this particular body, and let's suppose this T minus T infinity is called theta, and so dt will be d theta. Okay, so we can write this equation as minus HAS theta will be equal to rho CV d theta by dt. So we can rewrite this equation as d theta by theta is equal to minus HAS by rho CV into dt. So next integrate this particular equation. So we will be getting ln theta is equal to minus HAS by rho CV into t plus ln c, which is the constant of integration. So we can rewrite this equation as ln theta by c is equal to minus HAS by rho CV into t. So to eliminate this logarithmic term, we can take exponential on both sides. So we can write theta by c will be equal to e raised to minus HAS by rho CV into t. So this is the particular equation, and this theta is nothing but t minus t infinity. So let to determine this c, which is a constant, let's assume at t is equal to 0, and this t will be equal to t0, and theta will be is equal to theta 0, and this will be t0 minus t infinity. So applying this particular boundary condition into the above equation as at t equal to 0, theta 0 by c is equal to e raised to applying t is equal to 0, we can write e is equal to t is equal to 0, that is e raised to 0, and this e raised to 0 is nothing but 1, so we can write theta 0 is equal to c. So applying this particular constant into the above equation, we can write theta by theta 0 is equal to e raised to minus HAS by rho CV into t, and this is nothing but t minus t infinity by t0 minus t infinity. So this is the particular equation for this lumped capacity analysis. So let's move on. That is, see this particular exponential term, that is rho CV by HAS. Okay, so this equation is nothing but rho into C into V into 1 by H into AS. I am just rewriting this equation like this, and this rho CV is nothing but the specific heat or thermal specific heat, and this 1 by HA is nothing but the convective resistance, thermal resistance. So this rho CV by HAS, rho CV by HAS is nothing but C thermal into R conversion. And this particular term rho cv by hs is having the unit of time, so this term is called the dimensionless sorry I mean this is called the time constant and which is denoted by tau. Okay, this is tau, not rho. This letter is nothing but the tau. This is tau. So we can rewrite the above equation as theta by theta 0 is equal to e raised to minus t by tau. And this implication of this particular tau is what? The implication of this particular term tau is, as tau reduces, this exponential term will goes to 0, and then we can see that temperature of the body will reach temperature of surrounding very quickly. So that is the implication of this particular thermal time constant tau. So we need tau very small to get the body to reach the temperature of the surrounding very quickly. T reaches T infinity quickly. And also this HAS, the above equation, that is theta by theta 0, which is nothing but t minus t infinity by t0 minus t infinity is equal to e raised to minus HAS by rho cv into t. And this can be the implication of this particular equation, or the some reference that we can get from this equation can be, as t tends to infinity, this particular equation will become t minus t infinity is equal to 0. So which implies t is equal to t infinity, and that means as the time goes to infinity, the temperature of the body will reaches the temperature of the surrounding. And this can be represented graphically as this is the time t, and this axis is the temperature t. And suppose this is the point where the initial temperature of the body that is existing, and as the time improves, the temperature will vary exponentially like this, and this is the temperature of the surrounding, suppose. So the temperature of the body will be reaching the temperature of the surrounding in the course of time. So this initial difference between the temperature is theta 0, and for a particular point that is at the temperature t, we can find the theta like this. So this is the implication of this. This is a reference that we can get from this particular equation. Okay, so next we will be dealing with this particular term HIS by rho cv into t, and we can rewrite this equation as h into L square into t by rho into c into L cube. So cancelling this L square term and L cube term, we can write this as h L by k into t by rho c into L square. So I am just adding some constants and dividing some constants. So this can be further written as HL by k into k by rho c into t by L square, and this HL by k, let's write it like this, and this k by rho c is nothing but not k by rho c is nothing but the alpha, which is the thermal diffusivity, and it will be multiplied by t L square. So look at this equation, we can find that this HL by k is nothing but the Biot number, and this alpha into t by L square is nothing but the Fourier number. So we can write this particular equation theta by theta 0 is equal to e raised to minus HAS by rho cv into t as e raised to minus, this is e e raised to minus Biot number into Fourier number. Okay, so that's it. So we were dealing with some body which is at a temperature T, and in which or out of which some fluid is flowing at temperature T infinity, which is very less than that of the temperature of the body. So the to determine the net heat transfer, to find the total heat transfer that is occurring in the particular case, we can write this as Q will be equal to, and this total heat transfer is occurring from T is equal to 0 to T equal to Tf, as Tf is equal to Q dot dt. So this can be written as integral 0 to Tf. This Q dot is nothing but h into as into T minus T infinity into dt, and this can be further written as integral 0 to Tf h as T0 minus Tf into e raised to minus T by tau into dt, and this HAS into T0 minus Tf is nothing but a constant, so we can take it outside and we can write T0 minus Tf into integral 0 to Tf e raised to minus T by tau into dt. Integrating this equation, we can write minus HAS into T0 minus T infinity into tau into e raised to minus Tf by tau minus 1. Okay, and we know thus that this tau is minus HAS into T0 minus T infinity. This tau is rho Cv by HAS into e raised to minus Tf by tau minus 1. Okay, and we can cancel this HAS terms, and we can write this equation as rho Cv into T0 minus T infinity into 1 minus e raised to minus Tf by tau, and this is the net heat transfer that is occurring in the body.